Oh, thank you for the introduction and for having me here. So this will be remotely related to Sarnak's conjecture, and I'm not going to mention the conjecture in my talk, sorry for this, but there is some connection between these things. So let me start with a gentle introduction to the subject and explaining my objects and telling you what we are actually dealing with. So what you'll start with is your favorite subset of natural numbers, whatever you want. So this is the set B, and you build a corresponding set of multiples out of it. So you take all elements of your set and you multiply by all integers, and this is the object we'll be looking at. So we'll be looking either at the set of multiples or at its complement, which is called a B-free set. So this is the set of integers that has no divisors in set B. And for a good start, let us make a few simple remarks. So if a set of integers is close under taking multiples, then it is its own set of multiples. The second thing I want to say here is that B is called primitive if there are no redundant elements in this set. So if you have 2 and 4 in your set, 4 is redundant after you build the set of multiples. So you get rid of 4 and you get something nicer that gives you the set, the same set of multiples. So now a few examples. So if 1 is in your set, then this primitivized version contains just one element. The set of multiples is everything. The B-free set is nothing. So this is boring to study. So let us look at something more interesting. So now our B will be the set of squares of all primes, and FB are so-called square-free numbers, and the characteristic function of the set of square-free numbers is the square of the Möbius function. Well, some sequences here are one-sided, some are two-sided. I don't really care. So I like to work in this two-sided setup so that my maps are invertible. If something is not two-sided, just take the symmetric extension and you will get what you need to be in the same setup. So let me remind you, the Möbius function, this goes from z to -1, 0, and 1, whatever. So this is a symmetric extension of the function given by the following rules. So at 0, we have 0. At a product of k distinct primes, we have -1 to k. And if your number is divisible by a square of something, you put a 0. So this was the first interesting example. The second interesting and actually old example are abundant numbers. So a number is called abundant if some of its proper divisors exceeds n. And it is easy to check that it is closed under taking multiples. So it is its own set of multiples. And when you look at the complement, it will be precisely perfect numbers and efficient numbers. Something that has been studied and looked at for a long time. So specifically, in 1929, Besselhagen asked the following question: whether the density of the set of abundant number exists, and it was answered independently by these three people. The answer is yes. So the next question that comes up naturally is whether the natural density of any set of multiples exists. Here the answer is no, and was given already by Bezikovich in 1934. So his construction goes more or less like this. So he takes these intervals from tk to 2 times tk, and he takes the union, and well, this might not be primitive, so let's primitivize it so that it doesn't cause some technical problems. So this tk in his construction was a subsequence of 2 to k, but in fact it can be any sequence that it is increasing fast enough, and this construction will work. And then the upper density of the corresponding set of multiples is at least 1/2, and one can show that the lower density will be smaller than epsilon if your tk grows fast enough for this epsilon. Later on, it turned out that, okay, so natural density of a set of multiples might not exist, but there is a nice quantity that will exist, namely the logarithmic density, which is computed this way. And more than that, this is always equal to the lower natural density of any set, well, of this set of multiples. And also, when you truncate your set B further and further, and you build sets of multiples of these finite subsets of B, this will get, their densities will get closer and closer to this logarithmic density of your MB. And the last thing on the slide is a quite technical criterion which will be useful for me later on, namely the density of the set of multiples exists if and only if this strange limit is 0. So what do we have here? We have a sum over all elements of B that are between x to 1 minus epsilon and x. And then we look at the interval from 1 to x. We check whether our number is divisible by this A we are looking at. And we don't want it to be divisible but by anything that is smaller that is in B. So this is this quantity. Of course, you divide by x, and then you take lim sub over x, and then limit as epsilon goes to 0. So there is this technical criterion. Okay, so very many sets B that you can start with. And it's clever to look at different subclasses that will give you different properties and different dynamics. Okay, so we say that B is Bezikovich if this natural density of the set of multiples exists. We say that B is thin if the sum of reciprocals is finite. And we say that B is R dash if B is infinite, pairwise coprime and thin. So for example, this holds for B equal to the squares of primes. And there are 3 more, sorry for this. In a second, you will get a picture with relations of these notions. So then we have something kind of opposite. So we say that B is Berend if the density of the set of multiples is equal to 1. So for example, if you take all primes, in your set of multiples, you'll have everything. And you can also take subsets of those, and there are other variations. So these are Berend sets. Then we have Todt sets. So I started this talk with telling you that if you have 2 and 4, then 4 is redundant. But actually something more subtle can happen. So if you start with the set of all primes, and if you just remove one of them, then you will still get almost everything in your set of multiples. So to be more precise, the logarithmic density will not change. And we say that B is Todt if every time when I remove one element of my set B, then the logarithmic density of the corresponding set of multiples drops. So kind of every element is important from the point of view of this logarithmic density. And it turns out that this is equivalent to the following. So B cannot contain any rescaled copy of a Berend set. So to be Berend and to be Todt is kind of on 2 other ends. And the last thing here is minimal sets. So B is minimal if for any n there exists a natural number S such that this infinite arithmetic progression n plus SZ is either entirely in the set of multiples or it is sitting in the B-free set. So in other words, when you look at the characteristic function of B-free integers, the sequence that you get will be a Teplitz sequence, if you prefer that. And okay, the promised relations. So for this is the picture for primitive sets B. So these are all primitive B's. And you can see clearly that Berend sets are far away from anything in here. So this is what it looks like. So there is a clear description what is included in what. There are examples of anything. I mean, any area that is in the picture contains examples. There are no empty regions in here. Okay, so what about the dynamics? Now I will talk about the B3 subshift and its relatives or friends. So given set B, we define eta, which is the characteristic function of the set of B3 integers. So this is a 0, 1 sequence. I put a 0 if my n is divisible by some b, and I put 1 if it's not divisible by anything. And once I have a 0, 1 sequence, I can study its orbit closure under the left shift. So this is my B3 subshift. And now if B is R dash, so you can think of these squares of primes. So B is infinite pairwise coprime with summable series of reciprocals. It turns out that the B3 subshift is hereditary. So what it means is that if you take a sequence in your subshift, the 0, 1, so a 0, 1 sequence that is sitting there, and you start replacing some ones by zeros, you'll be still in your subshift. So you're allowed to take sequences that are smaller or equal coordinate-wise from what you have, and you will not fall out of the system. So if B is not R dash, then X eta might not be hereditary anymore, so it's clever to consider the hereditary closure. So the smallest subshift that is closed under this operation of taking things that are smaller than what you already have. And there is one more subshift that appears naturally in the setup, namely the B admissible subshift. So these are all 0, 1 sequences, such that when you look at their support modulo each B, there will be at least one residual class missing. So in other words, the sequence that you have arrives this way. You put arithmetic progressions of 0 of distance B somewhere for each B, and you fill in the rest with whatever you want. And since eta is an admissible sequence, eta is in this XB, it means that the B3 subshift is a subset of the B admissible subshift. So we have this inclusion. And now the admissible subshift is hereditary. I told you can put in between whatever you want between these mandatory arithmetic progressions of zeros. So this gives you this sequence of inclusions. If B is R dash, then actually the three subshifts agree. If it is not, these equalities may break in whatever configuration you want. I mean, there are examples. And what is interesting here is that the dynamical properties of these three subshifts correspond to number theoretic properties of MB and FB. So I started my talk with pretty old results, and now I'm jumping to something more recent, and I'm trying to tell you that there is a nice connection. So for example, B is R dash if and only if the three subshifts agree and the topological entropy is positive. Or B is Berend if and only if the B3 subshift is proximal and the entropy is 0. So there is an interplay between these two approaches. Okay, so I want to concentrate mostly on dynamics. So I need to introduce something called the Mirsky measure. So what is this? So if B is R dash, so squares of primes are your example that you should keep in your head, then the characteristic function of B3 integers is a generic point. So this sequence of measures converges to something, and we call this something the Mirsky measure. So since eta is a 0, 1 sequence, so what we do is we basically look at frequencies of blocks appearing on eta. This measure is ergodic and has full support. So this is a nice measure. In general, eta might only be quasi-generic. Of course, any sequence is quasi-generic for something, so I need to be more precise here. So if Ni is a sequence such that this quantity converges to lower natural density of MB, then this sequence of measures will always converge to the same thing, which we can call the Mirsky measure. So that's the quickest way to define this measure, maybe not the most natural one. So there is another approach more of an algebraic flavor. Namely, you define group G as this product group of residue classes for each B. And then it contains a closed subgroup H. So this is the smallest closed subgroup containing element 1, 1, 1, 1, 1. So this is what it says here. In other words, if R is the rotation by 1, 1, 1, 1, 1 on G, then H is the orbit closure of 0 under this rotation. So there are these two ways to view H. And in H, there is a special subset called the window. So this is the set of elements which on all coordinates have something else than a 0. Okay, I need one more thing. I need a coding function. So this is the function from H to 0, 1 to Z. And what it is doing, it is coding orbits of points under this rotation with respect to my window. So I'm taking my H, I'm checking if it's in the window or not. I'm putting either 1 or 0. Then I rotate, I check again. And this is how the image of phi arises. And now this group H has one invariant measure under R, namely the Haar measure. We can define the Minsky measure as the image of Haar measure via this coding. So depending from which background you come from, you have two choices, and of course one has to prove that they give you the same thing. Okay, so in the beginning of my talk there was this list of notions and this picture, and they were defined without using any dynamics. And now I want to look at these notions more dynamically. So let me remind you that B is thought if each element of B is important from the perspective of logarithmic density. So that was the definition. And there is the following result. So for any B, there exists a unique thought set B prime such that there is this inclusion between the corresponding sets of multiples and the logarithmic densities will agree. And actually the conditions on the set of multiples of this thought set can be replaced by the condition on the Minsky measures. Okay, so to be more precise, what is this set B prime? Well, you need to start with your B, you add something and you primitivize it. So what is this something? The something is a set of certain scales, namely the scales that kind of make your set not taut. So to be taut is not to contain rescaled copies of Behrens sets. So now I'm looking at where it breaks. I'm extracting these scales. I'm adding it to my set B and I'm primitivizing it. So this is exactly what the set B prime is. And we have the following. So B is taut if and only if B is primitive and there are no such scales. So that was already somewhere between the lines on the previous slides. Okay, so this was already there. There is something similar, which is just as important. So you will see in a second why this B prime and this B star, which I will define now, are important. So B is called minimal if eta is a Toeplitz sequence. So that was this inclusion of arithmetic progressions either in MB or FB. And we can define B star as follows. So again, we add to B certain scales and we primitivize it. The difference between this and between what we did before is that now we are looking at scales of infinite pairwise coprime subsets. And the set of scales C, which we used previously, is contained in this D, as any Behrens set contains an infinite pairwise coprime subset. And we have a similar statement to that about tautness. So B is minimal if and only if the set of scales D is empty. And this happens if and only if the B-free subshift is minimal. So this kind of justifies the name minimal for such sets B. There is more to this minimality business. Namely, it turns out that each B-free subshift is essentially minimal. And in fact, this unique minimal subset is again a B-free subset for a new B. For which B? Well, for this B star I have just defined for you. So there is a nice structure in there. Okay, so actually there is more than that. So we have the following joint strengthening of this inclusion. So this is about this unique minimal subset. And we have this inclusion of sets of multiples for B, B prime, and B star. I mean, this has to be proved and was non-trivial. So you saw that there was like a bunch of people and an interval of years in there. This is more or less automatic. Once you know what B prime is, what B star is, you get these inclusions. But it turns out that actually you have the inclusion of B3 shifts. So this X eta star is the smallest one, X eta prime is intermediate, and this X eta original B3 subshift is where all of it is happening. Okay, I want to add some more words to the explanation why we call these sets B minimal. Namely, there is the following result. So suppose that C is taut, then the corresponding, well, C3 subshift is a subset of X eta if and only if we have these inclusions on the level of sets of multiples. So in fact, this implies inclusions on the level of subshifts. And this leads us to the following definition of a certain partial order on taut sets. So C1 is preceding C2 if the corresponding C1 free subshift is a subset of C2 free subshift. And it turns out that minimal sets are precisely the minimal elements of this partial order, and B star and B prime are the smallest and the largest elements in the set of all taut sets such that the C3 subshift is sitting in our subshift. So I think this is justified well enough so that I can say that these B's are minimal, even if in the beginning it was like seemed random. Okay, so you have the background. So what about the motivation for what we were doing? There are two parts. So the first part is the following. So it is not hard to show that if the density of this tautification of the set of multiples corresponding to tautification exists, then the density of the original set of multiples exists. That's kind of straightforward. And unfortunately, we managed to quote it in the wrong direction in a paper with those people. This wasn't a disaster, so it was kind of easy to fix, but it raised the question, can actually all triples encoding the information whether these natural densities occur, can they, whether these densities exist, actually occur? The answer is yes, so that's a bit of a spoiler, but I will tell you why later on. And the second part is as follows. So Gerhard Keller formulated a certain conjecture on the form of the set of invariant measures of B3 subshifts. So I will not tell you now how this conjecture looks like. It's a bit technical. Well, we proved it, but we proved it in a different way than we originally planned. So we were thinking that we could prove the conjecture first for taut sets and then pass to the general situation by proving that upper Banach density of this difference is 0. So question 2, is it always true? Spoiler, no. Okay, so these are two parts of my motivation. These two questions seem different, right? So let me try to convince you that there is a common approach to these two questions. Okay, before I do that, let me formulate the results. So theorem A says that for any taut set, there exists a Bezikovich set B, so a set whose set of multiples has density such that C is precisely the tautification of B. And also for any minimal set D, there exists a Bezikovich taut set such that D is B star. So we kind of want to do a reverse procedure now. So before it was B, and I derived B prime and B star from it. And now I start with, well, I want to start either with B prime or B star, construct something that gives me those and has some extra properties. So for any taut non-Bezikovich set C, there exists B such that B prime is equal to C, and such that the upper density of this difference is positive. So actually, I mean, that's a disaster from the perspective from point 2 on this slide, right? It's not only upper Banach density, it could be even upper density. So this proposition C is in fact consequence of theorem A, but also has a simpler proof. So that's why I stated here separately. And then one can wonder, okay, in proposition C, this taut set we start with is non-Bezikovich. So the corresponding set of multiples has no natural density. So do we have examples where everything has density? And it turns out that one can construct a set B such that both B and B prime are Bezikovich, but nevertheless the upper Banach density of the set of multiples differs. Okay, so how to get there? The key is unions of rescaled patterns. So let me remind you, before we had this B, B prime, B star, and both B prime and B star were constructing by looking at certain scales, adding them, and primitivizing the whole thing. So this written here. So this E is the set of all elements such that a rescaled copy of some set A satisfying extra conditions sits in B. So we'll consider sets that are unions of EI times AI, where we think of EIs as scales and AI as patterns. These AIs will be sitting in a subset of primes in such an arithmetic progression, and we'll need that the elements of AI are large enough. And about E, which is the union of all these EIs, we'll assume something extra, namely either that this set is taut or minimal. And additional properties of these scales and patterns will result in additional properties of B, B prime, B star, I mean, whatever you need at the moment. Okay, so the main tool that allows us to control tautification and minimization is as follows. So if E is taut and AI are Barron sets, so for example, AI is the set of all primes in this interval, or all primes in this, well, all primes in this arithmetic progression in this interval, then E is equal to B prime. And now if E is minimal and AIs are infinite pairwise coprime sets, then we get this minimal, this start counterpart. Okay, so let me tell you something more about this upper Banach density of this difference of sets of multiples. So there is the following proposition, which is a refinement of proposition C, and it uses Davenport and Erdős theorem. So if E is non-Bezikovich, then for KIs that are sufficiently large, if B is of the form as before, so these scales and patterns and the union of those, where EI is just the intersection of E with interval 1 to KI, and AIs are large, then the upper density of these sets of multiples will differ. Now, I need to make sure that this B prime will be equal to E. So for this, we just assume additionally that E is taut and AIs are Barron sets, and we get where we want. So what about proposition D? I told you that this is maybe not the best example because one of these sets is not Bezikovich. So if both B and B prime are Bezikovich, then this upper density of the difference is precisely the difference of the densities. And the difference of the densities is the same as the difference of logarithmic densities. And they are equal because this is what we wanted from this B prime. So this is 0. So if both of them are Bezikovich, you cannot have hope that the upper density will be positive, but nevertheless, the upper Banach density can happen to be positive. And we were able to construct a thin and therefore Bezikovich primitive set E such that for Ki large enough and the set B being the union of products of scales and patterns, this holds. And again, we need to make sure that this B prime will be equal to E, so we assume additionally that these AIs are Behrend sets. Okay, so that was about question 2. So how is this whole setup of patterns and scales related to question 1? Well, I can tell you more or less how to construct examples. So I, j, k equal to 1, 1, 1. So I want all three, B, B prime, and B star to be Bezikovich. This is simple to achieve. So if B is f dash, for example, squares of primes, then B is automatically taught. So B is equal to B prime, and B star is just a singleton containing element 1. Why? Well, B is infinite and pairwise coprime, so it contains itself. So it contains itself rescaled by 1. 1 is in the set of scales, and that's how we get this. So that was easy. Now, ijk equal to 0, 0, 1. So now I want B and B prime to be non-Bezikovich and B star to be Bezikovich. So I start by taking G from this class of Bezikovich examples where you have this union from Tk to 2Tk. By Bertrand's postulate, G contains infinitely many primes. So this means that 1 is a scale sitting in D, and therefore B star is just the singleton. So it suffices either to take B equal to this G or B equal to its totification. Okay, so how to get 0, 0, 0? So I want all these sets of multiples not to have natural density. So Keller gave examples of non-Bezikovich minimal sets B. So here we just have 3 things that are equal, and the corresponding set of multiples fails to have natural density. Then we get to 1, 0, 0. So we want B to have MB to have density, and MB prime and NB star not to have density. So now we start with a non-Bezikovich minimal set. We had that on the previous slide. And theorem A tells us that there exists a Bezikovich set B such that E is equal to B prime. So B is Bezikovich, B prime is equal to B star, and it's non-Bezikovich. So how to see this equality? Well, B star is equal to B prime star. This is something small that you have to prove, but it holds for any B. Now B prime is equal to E, so I'm substituting for this B prime set E. And now E was minimal. This means that E star is the same as E. Okay, 2 more to go, you'll survive. So ijk equal to 1, 1, 0. So now E is a non-Bezikovich minimal set. And now we use theorem B to make sure that there exists a Bezikovich taught set B such that B star is equal to E. So what do we get? Well, B is equal to B prime because B was taught, so its tautification is the same set. So this is Bezikovich, and B star is equal to E, which is supposed to be non-Bezikovich. And the last one here, so we want this middle one to fail to have natural density. So we start with Bezikovich example E again. And theorem A tells us that there exists a Bezikovich set B such that B prime is equal to G prime. I guess it should be G in here. And then again, you can look at these things and check, okay, B star is the same as B prime star. This holds for any B. Now B prime is the same as G prime. And G prime star, what is this? This is the same as G star. I forgot it, but this G star is just the singleton 1 because it contains infinitely many primes. So 1 is in the set of scales. Okay, so some more details. How much time do I have? 10 minutes. Okay, so how do we prove this? So the theorem is as follows. So for any set E, there exists Ki such that if AIs are sets of primes sitting in these arithmetic progressions and are large enough, then set B built this way will be always Bezzikowicz. So scales are simple. They contain only one element. It's EI each time, and AI is a certain subset of primes. And if we additionally assume that we started with a primitive set, then these KIs can be chosen so that the resulting thing is again primitive. The proof uses the following version of Mertens' theorem. So it estimates the sum of reciprocals of primes in arithmetic progressions. It looks like this. So this phi is now not the coding function, but the Euler-Toshen function. And this allows us to get the following refinement of theorem A. So if we additionally assume that in this construction AIs are Behrens sets, then B prime is necessarily equal to E. And we also get a refinement of theorem B. So if additionally to these assumptions, we know that each set AI is R dash, then B star is equal to E. And additionally, if we know that the union of these subsets of prime is scarce enough, if the set is thin, then we will know that B is taut. So for example, yeah, I already said that. So you don't take too many and you get what you need. Okay, so even more details. So this is our goal. So we want to show that this set B is Bezzikowicz, and we will be using this complicated F- criterion. So we need to look at such expressions. So the density of set MB exists if and only if this limit is equal to 0. So we fix our set E, we fix our AIs, so these subsets of primes, and we denote by this MXAA, this thing that we have here. And this is what appears in R dash formula. So we have to be able to estimate this. So the first estimation is just looking at each part from this union separately. So this is easy. And the second step is to split this infinite sum into two parts that we can control. And we will use different arguments for this finite part and different arguments for this infinite part, where we split at I0 satisfying this condition. So there is always an I0 suitable for the epsilon that we have at the moment. So we want to estimate this first sum. So what do we have? So this is the expression from R' criterion. And we basically ignore this B here. So this quantity checks how many numbers you have between 1 and x that are divisible by EIA and that are not divisible by anything smaller. And I'm ignoring this part, not divisible by anything smaller. So if I do this, I get this rough estimate, and then I can go with it even further. So these A's are certain primes. So instead of looking at certain primes, I can look at all primes that are in here, or even all primes that are in this arithmetic progression and in this subinterval. And when we have this, we are able to use Mertens' theorem for arithmetic progression to get such nice bounds. The constant, which is in here, does depend on I and epsilon, but it doesn't depend on the choice of Ki, which is important later in the proof, that we can play around with Ki independently. And this in turn implies, and by this I mean there is work to do, but a first-year student should understand it. So there are some standard analytical computations that give you this estimate. And finally, you plug this in and you get that this finite sum is smaller or equal than to epsilon. Okay, so what about the second sum? So here the trick is to, instead of looking at this interval, to look at such a union of crazy intervals. So there we have this inclusion whenever L is large enough, and by large enough, I mean this. And now one can show that if ki's are large, then this function g that also appeared before in here will be smaller than 1/4 to I minus 1 for every x. So we plug this in. So this first inequality is just by this inclusion of this interval in this union. We use this estimate that follows by the choice of large ki's. Then we get another estimate which follows by the choice of correct I0. And when you sum this up, you will get 8 epsilon. So what we wanted to estimate is actually bounded by 10 epsilon. And now when epsilon goes to 0, 10 epsilon goes to 0, and we are happy. So thank you very much.